You hear about the carbon footprint of oil sands all the time, right? But what does that actually mean? Today, we're going to get our hands dirty and run the numbers from the ground up. We're going to look at the fundamental physics, the thermodynamics that drive the emissions of a really common extraction method. And by the end, you'll see exactly where those numbers come from. So let's jump right in.
So what's really going on here? What's the fundamental reason these facilities have such a high carbon footprint? It's not just some random number, you know? It's the direct result of solving a massive physical and engineering problem. And here's the cool part. If you stick with me, by the end of this, you'll be able to run the calculation yourself.
Okay, so it all starts with one single, immense problem, the nature of the bitumen itself. Deep underground, this stuff is not the liquid crude oil you might be picturing. Not even close. In its natural state, it's basically a solid.
And this slide, wow, this really puts the scale of the problem into perspective. We measure thickness, or viscosity, in something called centipoise. So for reference, water is just one. That super thick peanut butter you have in the back of your pantry, that's around 100,000. But bitumen, sitting in the ground, starts at over 1 million centipoise. 1 million. It's just unbelievably thick. You simply can't pump it. It's not going anywhere.
So, what do? How do you solve that? Well, the answer is heat. A lot of heat. To get that stuff moving, to get it to flow so you can actually pump it, you have to completely change its physical state. And that means heating the entire underground rock formation to over 200 degrees Celsius. Only then does its viscosity finally collapse and it starts to behave like a liquid.
But how on earth do you deliver that much heat, thousands of feet underground across such a huge area? Well, the engineering solution is pretty ingenious, but it's also incredibly energy intensive. The answer? You inject high-pressure steam.
This process is called steam-assisted gravity drainage, or you'll usually hear it called SAGD. The concept, when you break it down, is pretty simple. You generate extremely hot, high-pressure steam on the surface. We're talking 340 degrees Celsius hot, and you pump it deep underground. This creates what's called a steam chamber that basically melts the bitumen. Then gravity does the work, allowing it to drain down to a lower well where it can finally be pumped to the surface.
So now we know how it's done. But we need a way to measure just how efficient this all is. How much energy does this actually take? Well, in the world of SAG, there is one metric, one number that rules them all.
And that metric is the steam-to-oil ratio, or SOR. It's a beautifully simple way to think about efficiency. It answers one critical question. How many barrels of water did you have to boil into steam to produce just one single barrel of oil? The lower that SOR number, the more efficient the whole process is.
So what's a typical number for this? Well, it definitely varies, but a standard industry average for SOR is about 3. Now, just think about that for a second. For every 1 barrel of oil that comes out of the ground, 3 barrels of water had to be boiled into high-pressure steam. This ratio, this is the absolute heart of the entire energy equation. Okay, so we have all the pieces of the puzzle now. We know the problem, the crazy thick bitumen. We know the solution, the high-pressure steam. And we have our key metric, the steam-to-oil ratio. So now, let's put it all together and actually run the numbers. This is where we figure out the real energy cost, step by step.
All right, let's walk through the math. First, we need to know the amount of energy it takes to turn hot water into that high-pressure steam. Physics gives us a hard number for that. It takes 2,328 kilojoules for every single kilogram of water. Okay, step 2. We've got to convert that to barrels because that's how we measure oil. A barrel of water has 159 kilograms, so we do some quick multiplication and we get about 0.37 gigajoules of energy per barrel. And now for the most crucial step, we apply our steam-to-oil ratio. We multiply that energy by our SOR of 3, and that gives us our final number. And here it is, 1.11 gigajoules. This is the minimum amount of raw heat energy that has to be delivered to the water to produce just 1 barrel of bitumen. This isn't a guideline or an estimate. This is a baseline dictated by the laws of thermodynamics. So we need 1.11 gigajoules of heat. But where does that heat come from? Well, it has to be generated. And in the oil sands, that almost always means burning natural gas. This right here is the direct link between the underground physics and the emissions you see coming out of the facility stack. Of course, in the real world, no process is perfectly efficient. The big steam generators they use are, on average, about 85% efficient. That means for every unit of energy you get from burning fuel, only about 85% of it actually makes it into the water as useful heat.
The other 15% is just lost to the environment. And to make up for that lost heat, what do you have to do? You have to burn more fuel. So we take our required heat of 1.11 gigajoules and we divide it by that 85% efficiency. And the result? The facility has to actually burn 1.31 gigajoules worth of natural gas for every single barrel of oil it produces.
And burning natural gas, as we know, creates carbon dioxide. When we apply a standard emissions factor to that combustion, that 1.31 gigajoules of natural gas results in approximately 65 kilograms of CO2 equivalent emissions. That's 65 kilos coming directly out of the facility's stack for every barrel of oil. This is the direct on-site carbon footprint.
But wait, the story doesn't actually start when the gas arrives at the plant. To get the full picture, we have to account for all the emissions it took just to get that natural gas to the burner in the first place. This is what we call the life cycle perspective. These upstream emissions include everything from extracting and processing the gas to transporting it through pipelines. But, and this is a big one, it also includes fugitive methane leaks all along that supply chain. And since methane is a much more potent greenhouse gas than CO2, you have to account for those leaks to get an accurate number.
So this chart here, this brings it all together. When we add those upstream emissions, our average number for an SOR of 3 rises to about 70 kilograms of CO2e per barrel. But what's really important here is to see how much it all scales. A highly efficient facility with a low SOR of 2 has a much smaller footprint. A less efficient one with an SOR of 4 has a much larger one. It all comes back to that one key metric, the steam-to-oil ratio.
So, when you ask why this whole process is so energy-intensive, this quote just says it all. You are not just moving fluid. You are fundamentally altering the thermodynamic state of a massive subterranean rock formation. I mean, think about that. You are injecting enough energy to change the very nature of a huge piece of the planet deep underground. And that, fundamentally, is where all these emissions come from.